All right, let's get started to make sure that we have enough time for the great talks we have lined up today. So first, just to introduce myself, my name is Paulina Czarnecki. I recently finished my PhD at Columbia with Robert Pincus and Lorenzo Polvani. I'm now a postdoc at IPSL, working primarily with Olivier Boucher and Nicolas Belouin. And I am joining the organizational committee for the ECS and Cloud Feedback Symposium. So just to briefly introduce the symposium, this is our 48th event. We usually start at 12 noon Eastern. There's 3 AGU-style talks. We're going to have some time for questions after each talk. And then at the very end, we'll have a general Q&A session for all the speakers to answer your questions. Today, we have Adam Bauer from the University of Chicago, Moritz Günther from the Max Planck Institute, and Clare Singer from the University of Colorado Boulder. If you have questions or comments during the talk, you can type them into the chat, or you can raise your hand and we'll call on you so you can ask your question. I just said that. You can raise your hand and unmute when it's your turn to ask your question. And this is our executive committee. We're always looking for more speakers and we're always happy to hear any feedback. So if you have any thoughts for us, feel free to email any one of us. And as usual, you can sign up for our mailing list, look at videos of old talks, and sign up for, find our contact information to give your own talk on our website. And I think that's what we have for the intro. So with that, we can get started with Adam Bauer. He is a postdoc at the University of Chicago. Adam, you can share your screen.
Yep.
And yeah, take it away.
Cool. Okay. Well, thanks so much to the committee for inviting me, and thanks for everyone for coming. This is really a full circle moment for me. Those who have spoken to me before, I was doing astro in my PhD, and I switched to doing climate about a year in. This is probably the first ever symposium I ever went to in climate stuff once I switched. So this is really a nice moment for me to, after I've completed my PhD, to actually give a talk here. So I'm super excited. Today I'm going to be talking about learning climate sensitivity from future observations, fast and slow. This was work done with Chrissy Protesescu, longtime ECS Symposium attendee, and Kelvin Drogemeyer, both at UIUC. So the motivation for this work really was born out of actually some consulting work I did at the World Bank for the last 2 years of my PhD. And why that is, I can't advance the screen. Hold on one second. Sorry. Give me one moment. Whoa. This has not happened before. Okay. Share. Let's try sharing Keynote. Okay, all good?
Yeah, that looks good.
Okay, cool. Sorry. Okay, so reason why this is happening, why we decided to pursue this question or this topic is that it's well known in this group and obviously in thinking about climate policy is that it's well known that the magnitude of climate uncertainty is important for any kind of economic models that you do of climate change. If you're in insurance, the amount of climate risk is going to set your premiums. If you're thinking about carbon taxes, it's going to set your risk premium. If you're thinking about investment strategies, any additional volatility is going to impact how you trade. And so the magnitude of climate uncertainty is really important when we think about climate economic models. However, I think that there's another angle to this that's more explored in the economics literature that's ever been really explored in the physical sciences literature, which is about the temporal evolution of climate uncertainty. And the reason for this is, there's a number of different studies that have looked at this dating back to 1999. Well, they'll make claims like, if we can limit TCR uncertainty, if we can have TCR uncertainty by 2030, that could be worth up to $9.3 trillion US. And you can make this estimate using an integrated assessment model. And indeed, Chris Hope made this estimate in 2015 that garnered a lot of attention. So to gain some intuition for why this is the case and why we decided to kind of take a stab at answering this question from more geosciences perspective than maybe an economic perspective, was if you imagine you have a 2-period model where before some date, you have to hedge against a number of uncertain futures. And then after some date, the uncertainty goes away and you can adjust your policy depending on what the true state of the world is, whether high ECS, low carbon budget, high carbon budget, et cetera. If your uncertainty resolves really quickly, you might have something that looks like this. So this is from a model that I worked on at the World Bank that's published in Earth Future in 2025. This is just for illustrative purposes only. If folks have questions about this model, they're feel free to ask. But here we're plotting the investment effort per year in trillions of dollars. The gray dashed line is the deterministic model, and the colored lines, the solid lines, are all the stochastic model. And so the black line is the pre-learning that before you get to hedge, during the period you're hedging against all these possible outcomes. The black line is that pre-learning path. And what we find is that the black line is really close to the gray line when you have no uncertainty at all. So there's very little hedging behavior in the model. After the uncertainty resolves and you have these different scenarios that the policymaker can adjust their policy for, you see the spread is not that big between the worst case and the best case scenario. Compare that to 2050 if the uncertainty resolves 20 years later. Black line really diverges from the gray line. You have a lot of hedging behavior. You have to spend a lot more money up front to be robust against all these future scenarios. And the spread between worst case and best case really starts to separate. So that's really, really costly. And so the mental model here is that the later your uncertainty resolves, the more persistent the uncertainty is, the more hedging and the more asymmetric risk there's in the problem, and that leads to more costly policies. So this is why in the economics literature, this is something that's kind of well understood. However, from the physical sciences perspective, any model you look at that thinks about these problems in the economic space all assume all of the climate uncertainty is really only captured by just feedbacks. There's no other uncertainties that are in the problem. And secondly, there's really no physical insight into what drives these learning rates that tells us, what are the key physical processes that drive how quickly we might learn about climate sensitivity, conditional on more observations in the future of the climate system. And so with that as background, the motivation for what this talk and what we're going to be talking about is first, we're going to try and build a more credible model for these learning rates, accounting for parameter covariances and trade-offs and estimating climate sensitivity. And the second thing we're going to do is try and use this model to build a physical understanding of what determines how fast we might expect uncertainty in ECS to go down, of ECS or TCR to go down in the future. And to give a snapshot of the results, what we're going to find is that we can constrain TCR reasonably well by the end of the century, regardless of whether we're in a high or low TCR world. But however, this robustness across true values is not the case for ECS. What we'll find is that for ECS, we can expect to have a robust constraint for low values, but not necessarily for high values. And the key physical driver here that we're going to find is that all of this boils down to what is the relative share of warming between the fast and slow climate modes in the both transient warming case and in the equilibrium warming case. So now we can dig a little bit more into what we did. So we approach this problem from kind of Bayesian perspective, imagining that there's a world where climate sensitivity is low, and we're going to try and estimate its climate sensitivity, and we can do the same exercise again where the climate sensitivity is high. So what we do is that if you imagine there's kind of two situations here, climate sensitivity is low, climate sensitivity is high. What we do is use our best knowledge of the climate system to project uncertainty. And then by assuming some model parameters that result in a lower high climate sensitivity, we generate some pseudo observations of the future, some pseudo data for the next 50 years or 20 years in this case for climate change. We're then going to use data assimilation to update our posterior estimate of climate sensitivity, of climate change, of climate uncertainty, conditional on this pseudo data. And we can do this iteratively to try and get a time profile of uncertainty evolution in time, conditional on these new data, and of conditioning on what the true value of ECS might actually be. On a technical level, what we're really doing is using the HEL two-layer model as our kind of climate models, our reduced complexity climate model, where we specify some true values of the different parameters within the HEL two-layer models. That sets our true ECS and our true TCR and so on. We can generate some noisy pseudo observations of future climate change, assuming some emission scenario. So for all the results that we'll show today, it's SSB2 4.5. And the observations that we're assimilating are both surface temperature and the ocean heat content. And we did check that it was robust to future other emission scenarios, and all the results still hold. So with those observations in hand, what we do is generate a number of samples from multivariate prior of all the model parameters that we have within our HEL two-layer model. And then minimize the cost function, the data assimilation cost function for each ensemble member. And the result of this is a maximum likelihood estimation of all the model parameters conditional on these future pseudo observations of the future. So we're getting a kind of maximum likelihood Bayesian update for our posteriors of our parameters conditioning on this new data. And so what do we find? Well, here what I'm going to show is on the left, the prior for ECS, and on the right, the prior for TCR. And the solid colored lines in these figures are the true values that we're trying to estimate. And so we're starting here, and the first year of the model is 2020. So by 2030, we have 10 more years of observations. And the color distributions are the posteriors for the different true values that we're trying to estimate. And what we can see is that the distributions are starting to spread apart, but there's still a lot of overlap. And as we go more in time, the distributions slowly but surely start to branch apart. We can do this all the way to 2100. Now, in 2100, the picture for ECS and TCR start to seem a bit different. For ECS, focusing on the left-hand side, if the true value is low, that is ECS is about 2, the yellow distribution is right on top of that solid line, meaning we're getting a robust constraint by 2100. However, when ECS is really high, the blue, the navy distribution, the green distribution are far away from the true values, meaning that we're really struggling to constrain upper values of TCR or of ECS. Comparing that to TCR, we find that all the distributions are really overlapping with the true values, meaning we're getting a really strong constraint on TCR. So for the rest of the talk, what I'm going to try and do is sketch out a physical theory as to why this is the case, why we can learn why we struggle to learn ECS, or the learning rate's kind of asymmetric across the true value, but for TCR, we have a robust constraint. And the reason is, and what we're going to do is to decompose the learning rate across the different climate modes. So what I'm showing is the prior projection in pink of the fast climate modes contribution to global warming. And the blue is the same projection, but with 30 more years of observations using our parameter posteriors. And each panel is for a true value of ECS. So what we're seeing across the board is that ECS is that we can learn the fast climate mode reasonably well, regardless of the true value of climate sensitivity. That's kind of lesson number 1, or key piece number 1. But the second point is that the deep ocean, the slow climate response, remains really is difficult to constrain across each of these true values. So we cannot learn the slow climate mode well, regardless of the true value of climate sensitivity. Now, how this translates to TCR and ECS, the additional piece of the puzzle is to look at how much warming is happening at which time that can be contributed to these different climate modes. So in ECS is 2, what we find is that there's the fast mode is the dominant source of warming in the near term. That should come as no surprise. But in equilibrium, actually the fast mode still is over 50% of the warming still comes from the fast mode, meaning that all of the information we're getting in the near term that's constraining the fast mode is really useful for constraining the equilibrium climate sensitivity when the climate sensitivity is low, when ECS is low. When ECS is 3, same transient picture, but now the slow and fast mode are more 50-50 for warming and equilibrium. And when ECS is 6, again, the fast climate mode is dominant, but the slow mode starts to become the majority of the warming for in equilibrium, which is why we can't constrain ECS when ECS is really high. So the lessons here is that most of the near-term warming is attributable to the fast climate mode, independent of the true climate sensitivity, which leads to robust TCR constraints across the board. However, in equilibrium, higher ECS values have more warming attributable to the slow ocean mode, which is difficult to constrain and therefore hampers our ability to constrain tail values of ECS, even with an additional 80 years of observations. So, take-home points that we have here. First of all, I wanted to stress the point that the timing of uncertainty reduction is really important for our decision-making and important for economic modeling. We then built a data simulation model to make the point that we can expect uncertainty about TCR, or transient climate metrics, to decline with new observations, but that picture does not necessarily hold for equilibrium climate metrics. And the reason for this is that for high values of ECS, the learning rate is hampered by our inability to constrain the deep ocean response. And so that's kind of the asymmetry here, is that most of the warming is happening, most of our constraints are coming from constraining the fast mode. That's really useful for TCR. It's only really useful for low values of ECS, and as you increase ECS, it becomes less and less useful for constraining ECS. And so I think I'm more or less on time. So thanks for your attention. There's a preprint out on archive if folks want to have a look at the full paper. Email and website if you want to get in touch. And I'm looking forward to answering your questions. Thanks so much.
Great talk, Adam. Gavin, I think, had a question first. Gavin, if you'd like to unmute.
Hi, thanks. So I actually have two questions, but the first
Sure.
one is, to what extent does this depend on what is actually driving things? What happens if there's a big volcano? What happens if the aerosol trajectory is outside the scenarios that you're using? There's
Mhm.
there's also a caveat because of the forcing, right?
Sure. So yeah, definitely true. I want to say that when we did this, in our forcing representation, we did force the model with both CO2 and aerosols, and the model is trying to tease apart the sensitivity of forcing. Let me see if I can find it. Yeah, so we have CO2 and aerosols both in the model, but of course, if there were some large shock, let's say from a volcano, that would change the quantitative results slightly, or would change the quantitative results. I still think the qualitative picture that the amount of warming you get between these two different metrics would probably still hold. The intuition would still be there.
But you still
Um,
have to have like a large increase in carbon dioxide, right? Because
oh,
if
sure, yeah.
we actually got to net zero tomorrow, and then we expect temperatures not to change at all, then there are no constraints on anything, right?
Oh, yes, yeah, 100%. Yeah. So we are
Wait,
assuming
so
that you'd
how
have
much does
some.
carbon dioxide need to be rising for this to even be a valid, even a pseudo constraint?
Well, that's a good question. So yeah, I'm not entirely sure. We never did the exercise of like, let's say you're on, 80% of SSB2 and so on and so forth, and see at what point do you lose your ability to constrain. That's a good idea. We didn't touch on that. We went basically we took SSB2 as the most realistic, let's say, expectation, and then tested with SSB5. But that would be a good thing. We should definitely check that.
Okay, thanks.
Yep.
Great. I think Rob Wood had a question.
I think
Yeah.
Gavin sort of, yeah, it sort of was addressed in the last comment. Yeah, thanks.
Great. Then Kristen is next.
Yeah, I guess this is this classic argument in economics, and I thought there's some consensus. So the more you invest in adaptation now, the less damage from climate calamity, from extremes and so on, you will have in the future, regardless of your uncertainty in the sensitivity. So maybe I got that wrong. Maybe you can, um, yeah, hammer that point home a bit more than that I understand it.
Yeah. No, so that's true. That's thinking about adaptation. The models I was specifically mentioning are thinking about mitigation, which is more upstream than that. So I think when you're thinking about adaptation, you're kind of breaking the link between temperature and damages. So regardless of your ECS uncertainty, you're always going to be limiting the amount of damages you're experiencing. But when we're thinking on the economic models I was specifically talking about, you're more thinking about how much should you invest and when, and that does depend to a certain degree on how much warming you expect to get. And so I think it's a different that logic is more specific to adaptation. I don't think it quite holds if you're thinking about mitigation specifically, but I'd be happy to talk more about it too.
Cheers.
Yeah.
Great. I think we should move on to the next talk for now. And then we can have a further discussion with Adam at the end. So our next speaker is Moritz Günther. He is a group leader at the Max Planck Institute. He will talk about heating the land and cooling the ocean.
Hi. Yeah, thanks. I'm presenting work that I did together with Sarah Kang and Yochai Caspi, and we were dealing with the problem that I've illustrated here on the left. And what you see there is the Pacific Ocean, which in the recent decades has warmed quite a bit over its western part, but it has actually cooled over the southeastern part. And it's a bit of a puzzle why this has happened and what's going to happen with this in the future. And we want to contribute to understanding what's going on there. To put this a bit more quantitatively, the models are underestimating the cooling in the southeastern Pacific, and you can see this quite clearly here in this figure that I've taken from Wills et al. 2022, where the observations show a cooling in the southeastern Pacific and in the Southern Ocean between 79 and 2020. And when models simulate the same period, they cannot just simulate this absolute cooling there. And Wills et al. Argue that theirs cannot be explained by internal variability alone. So in other words, there seems to be a persistent bias of climate models that they all share that prevents them from simulating this southeastern Pacific cooling. And I want to argue that we really want to understand what's going on there not just because it's a funny quirk of climate models, but because the Pacific temperature pattern influences, for example, radiative feedback, which makes it relevant for this symposium where we're concerned with climate sensitivity. It also influences patterns of precipitation locally and globally, and it influences the formation of tropical cyclones. And there is quite a body of literature that examines mechanisms that influence the Pacific sea surface temperature pattern. There's a nice review paper by Watanabe et al. From 2024, where they show all kinds of mechanisms that influence the pattern here. So there are some, you don't need to intake everything here, just see how diverse this is. So there are some local processes like the cloud feedback, but also remote influences from other ocean basins. There is influence from the deep ocean. However, what's completely white in this figure is the land, which there is sometimes this understanding that land doesn't really play an active role in this system, and it just follows what the SST tells it to do. And I want to show a little bit of a different perspective on this and show that land heating also actively influences the Pacific temperature pattern formation. So what we did in order to demonstrate this, we performed simulations with MPIESM, which is our CMIP6 type climate model. And the simulations that I ran for 10 years, and I always perform 24 ensemble members. And everything I'm showing to you is an ensemble mean. So we're really looking at forced response and not some kind of internal variability. And all simulations are abruptly forced. So the first example is this 4x CO2 simulation that we've all already seen 100 times. But the more interesting ones are simulations where I prescribe 4x CO2 forcing only over the ocean or only over land. And it's important to note that in these simulations, CO2 is really fixed in time. So the spatial pattern remains. It's not somehow transported or taken up by the ocean or anything. It just remains like this. And of course, with respect to land temperatures or land sea contrasts, this 4x CO2 land simulation is going to be the more interesting one. From the perspective of forcing, I think it's clear that 4x CO2 over ocean plus 4x CO2 over land adds up to 4x CO2 everywhere. But it's less clear that this also holds for the climate response to this. So this is the first thing that we checked. I'm showing here the temperature response, 2-meter air temperature, in the second year of the simulations. And all I want you to notice from these two panels is that 4x CO2 forcing everywhere is really hard to distinguish from the response to 4x CO2 over ocean plus the response to 4x CO2 over land. So this linearity holds surprisingly well, and we can actually look into this decomposition in a meaningful way. And then the more interesting stuff appears when we look at the simulations in isolation. And the first thing that catches my attention here is in response to 4x CO2 forcing over land, we get this pronounced cooling over the equatorial and eastern Pacific Ocean. So in other words, if you add heating to the land, the system seems to react with cooling over the Pacific Ocean. And most of the remainder of this talk is going to try to explain where this cooling comes from. I'm not going to talk too much about this ocean simulation here. I just want you to notice that when we force with 4x CO2 over ocean, there is an enhanced Eastern Pacific warming, so what we would call an El Nino-like warming. But I'm coming back to that a little bit later. So we identified 3 mechanisms how land warming induces Eastern and Equatorial Pacific cooling, and I'm going to go through them one by one. I'll have to rush a little bit because I actually have a little bit less time than I thought when I prepared this talk. There is a northward shift of the ITCZ, a westward shift of convection, and a strengthening of the subtropical highs. And eventually all of these mechanisms are related to how winds change and how this can cause a cooling in the Eastern Pacific. So the first one is the northward ITCZ shift. And the way we identify these mechanisms is by only forcing parts of the land. So in this case, we only force Northern Hemisphere land north of 8 degrees north. So everything in this magenta outline is forced with 4x CO2. The rest is at 1x CO2. And so there is no local forcing adjacent to the equatorial or southeastern Pacific. And yet we see almost the same cooling patch appearing that we saw in the simulation with 4x CO2 forcing over all land. And so that means that there must be a teleconnection from the northern hemisphere to the southern hemisphere, just that the cooling here is about 50% weaker than what we saw in the other simulation. So it's only part of the story, but it doesn't explain everything. And we explain this with a northward shift of the ITCZ. So it's actually quite well known that if you put more energy into one hemisphere than the other, then the ITCZ has to shift to the warmed hemisphere. And that goes together with a strengthening of the southeasterly trade winds in this case. So in this case, the ITCZ would shift north, and the southeasterly trade winds here would strengthen, which causes more evaporative cooling over the Eastern Pacific. And once this cooling perturbation reaches the equator, it's then communicated throughout all of the equator via the Bjerknes feedback. The second mechanism has to do with the shift of convection. So here the strategy is the same. We only force part of the land, and this time it's all tropical land between 8 degrees north and 8 degrees south. So from this perspective, there's no reason to expect a northward ITCZ shift due to energetic reasons. And yet again, we find the same cooling patch that we've seen before. This time again, it's weaker than in the simulation that forces all land. So this is again contributing part of the full story. And we explain this with the fact that when you put tropical land forcing, the convection will shift westward. And the reason for this is that the main balance in the tropics is between diabatic heating and vertical motion. And so if we add diabatic heating over land, you can see how this increases the upward velocity at 500 hectopascal. So you see this nicely over the maritime continent and also over the South American land here. And this increased convection over, for example, the maritime continent goes at the expense of convection in the Western Pacific warm pool. And so this whole circulation pattern is just shifting to the west. And this is basically the same thing that we observe on interannual timescales during a La Nina. So also during La Nina, the whole convection pattern shifts to the west. And you can even see very nicely here the Kelvin wave response on these equatorial easterlies that develops in response to this enhanced convection over the maritime continent. Last mechanism is related to a strengthening of the subtropical highs. So for this, we only put the 4 times CO2 perturbation over South American land. And this does something that is actually quite comparable to what happens every year during the South American monsoon. So in austral summer, when the South American monsoon kicks in, you get a lot of diabatic heating from the latent heating over South America, and this strengthens the subtropical high in the South Pacific. And again, when you strengthen this subtropical high here, the geostrophic winds are going to become more southeasterly, and that causes a strengthening of the evaporation and also cold advection from higher latitudes into the lower latitudes. I want to briefly talk about timescales of the response. Everything I showed to you until now was from the second year of our simulations, and the absolute cooling that we see in the 4 times CO2 simulation with forcing over all land actually disappears after about 5 years. So you might argue that maybe this is not really relevant for the cooling that we observe on this multi-decadal timescale. But I want to argue that on these abrupt force simulations, the timescales work a bit different from what we see if we have a transient forcing. And so in order to show this, I performed this simulation with 1% CO2 forcing per year over land. So it's the same as before, but now ramped up more slowly. And what I'm showing here is the 2-meter air temperature trend over 20 years. And so all I'm trying to say here is if you ramp up the forcing more slowly, then actually the cooling can persist for several decades and doesn't disappear after 5 years or so. I think I have to be a bit quick with my comments over the ocean thermostat. So I'm not going to explain what the ocean thermostat mechanism is. So this is just, if you know what the ocean thermostat mechanism is, then this might be interesting, because I think that our results are a bit hard to reconcile with an active driving role of the ocean thermostat mechanism. Because the ocean thermostat mechanism would predict that in response to a uniform forcing over ocean, the ocean would react with an enhanced cooling in the Eastern Pacific. But what we actually find in our 4 times CO2 ocean simulation is an enhanced warming of the Eastern Pacific. So this is the opposite of what the thermostat mechanism would predict. On the other hand, if you go into a heat budget decomposition of the mixed layer in this land force simulation where we do see cooling, these upwelling terms actually show up being important. So I don't want to just say that the ocean thermostat mechanism exists or is not relevant, but my current interpretation is maybe that we should view it more like a feedback rather than a driver of this cooling. A little bit like the Bjerknes feedback that just amplifies whatever perturbation you give in. But I don't know, maybe this is controversial and maybe we can discuss this also in the end. Quickly want to mention that also other feedback mechanisms are really important in amplifying this cooling. So we can show that the west feedback and the cloud feedback are really necessary to get this pronounced cooling patch. And if they are not active, then the cooling wouldn't be as strong as what we find here. Now, what does this tell us about our model observation discrepancy that I motivated this with? I think that this kind of gives us a list of mechanisms that we can go through. And if models represent any of these mechanisms wrong, then the cooling that we would want to find in response to land-sea contrasts will be underestimated. And so I just mentioned that cloud feedbacks are important and that ocean upwelling is important to get the response right. I also said that there is this mechanism that depends on the ITCZ shift. So if the ITCZ structure is misrepresented, then this mechanism is not correctly there and we would get the wrong cooling. And also convection has to be represented well in order for these mechanisms to work. And we know that CMIP models parameterize convection. So there's quite some potential for misrepresentation here. I think none of these are really surprising. I would call these the usual suspects of what people typically say when they talk about this model observation discrepancy. What is really a new aspect here is that there's also a need to scrutinize uncertainties in land models. And in fact, there is a postdoc in my group who's currently showing that CMIP6 models underestimate the land warming or the land-ocean warming ratio. So there might be a little bit more to this. Let's summarize. I hope I could convince you that heating over land causes a fast cooling in the Eastern and Equatorial Pacific. I've shown you that there are three mechanisms which are all related to strengthening of the winds, especially the southeasterly trade winds in the Pacific. One is the northward ITCZ shift. The second one is a westward shift of convection. And the third one is related to the strengthening subtropical highs. In my opinion, we should view the ocean thermostat mechanism more like a feedback than a driver. And if there's one message I can choose for all of you to take home, then it would be that land really actively shapes temperature pattern formation in the Pacific Ocean. It's not just a slave to the ocean, and we should really give it the attention that it deserves. So yeah, thanks a lot.
Great, thank you. That was an amazing talk. It looks like we have a question in the chat from Karsten.
Yeah. First off, Moritz, great talk, great results. Funny that I haven't seen that before. Not sure anyone ever did it, but it looks cool. But when you showed land only, it did remind me a bit of this interhemispheric temperature contrast that you get increasingly over the last couple of years between the hemispheres. So summer, northern hemisphere, Pacific, and Atlantic warms a lot faster because the mixed layer is shallower. And so you get this additional temperature gradient, which, must project on the circulation as well, and vice versa in northern hemisphere winter. Might that also play a role here?
So I'm not sure I fully got it. So you say there is a seasonality in the warming pattern, or?
There is increased seasonality in the ocean interhemispheric temperature contrast, if you like. So summer anomalies are much higher now in the northern hemisphere over the ocean than they used to be. And so then things cool down in winter to kind of normal anomalies because of much more mixing and so on. And so that changes the temperature gradient. And
I'm not
I think
sure.
that might play a potential role. I don't know.
Yeah, I'm not sure. I think I would have to think about it a bit. But there is a paper that shows that for these northern hemisphere temperature anomalies to really reach the ITCZ and shift the ITCZ northward, it takes something like 3 years. I think this is a very rough estimate from the pattern. But so maybe if this changes on seasonal time scale, it might just be, that might not make it to the ITCZ. So I'm not sure. I'm not sure about this. I'd have to give it a look. Could be, could not be.
All right. Thanks.
Great. Let's start with our third talk, and of course, feel free to continue discussions in the chat or save your questions for the last few minutes. So our final talk will be Clare Singer. She is a postdoc at the University of Colorado Boulder, and she'll talk about the Southern Ocean.
Okay, excellent. Thanks so much, Paulina. And yeah, thanks to all the organizers. Like Adam said, this has been just a great seminar series to get to interact with over many years. So I'm excited to speak to you all today. So this is work that I did at Lamont with Robert Pincus during my postdoc, so supported by NOAA Climate and Global Change Fellowship. Many thanks to that great program. And yeah, it was just recently published at the end of December. So this is the title of the paper. It's rather verbose. I'm going to start off by first describing what is this term at the end, the hemispheric albedo symmetry, and then talk about, kind of give you some inspiration for why it's important, show you that it might be changing, and then talk about what we think is part of that cause coming from Southern Ocean aerosol. So this observation that the albedo is pretty much identical between the two hemispheres is quite surprising and quite striking. So the overall reflection from each hemisphere is about 100 watts per meter squared, and the difference in reflection between the two hemispheres is 0.01 watts per meter squared. So that's kind of integrated over the whole hemisphere. What this plot is showing is the difference in shortwave reflection for each latitude, northern minus southern. And each of the thin lines is one 12-month running mean over this observational period from Ceres. And so we can see that in some latitudes, the northern hemisphere is brighter, more reflective, and some, the southern hemisphere is more reflective. Sorry if you could hear my cat running around in the background. So if we can break that total reflection down into contributions from different parts of the system. So green is showing reflection off the surface, pink from the atmosphere itself, and blue from clouds. And by doing this, we can start to understand some of these features, like the brighter northern hemisphere in the tropics is because of the mean position of the ITCZ, and the brighter southern hemisphere in the mid-latitudes is because of the more cloudy storm tracks. We can see that Antarctica is much brighter than the Arctic, and that throughout kind of the entire subtropics and mid-latitudes, there's more land and also more aerosols in the northern hemisphere, both coming from the land surface and from people living on the land. But overall, when we look at this from a hemispheric perspective, the contributions from the surface and clear sky atmosphere, so the clear sky components perfectly cancel out the cloud components. And so this is quite surprising. There's a number of people who are listening right now who have thought about this, but there's still no really a priori expectation for why this symmetry should exist. And what I wanted to start looking at was kind of how robust it's been over our observational period. And so we know that over the Ceres period since the start of this century, the albedo in the global mean has been decreasing, so less reflected shortwave radiation in total. And that has been driven pretty much entirely by clouds, both the interannual variability and also this long-term trend, with a kind of small contribution from decreased reflection from the surface, melting ice primarily. But overall, this kind of global mean dimming has been pretty symmetric between the hemispheres. They're kind of dimming at roughly the same rate. If we look at that more closely, though, we see that this asymmetry, or the difference in reflection between the hemispheres, is not perfectly stagnant, and that it has been decreasing over time. So meaning that the northern hemisphere has been dimming slightly faster than the southern hemisphere. And although the clear sky in the global mean is contributing pretty much zero to that trend, it's really the dominant driver of this change in the antisymmetric component. And that is because in the clear sky, so here I'm plotting the trend in clear sky reflection, the northern hemisphere has been dimming, but the southern hemisphere has actually been brightening. And so in the global mean, this cancels out, but when we look at the asymmetry, this kind of is a doubled effect. We know that what is actually doing this reflection of shortwave radiation in the clear sky atmosphere is mostly particles, aerosols. And so it shouldn't be too surprising that the trend in this clear sky reflection looks very similar to this trend map of aerosol optical depth. But this is also kind of a good confirmation in these observations that are coming from different instruments, from Ceres and MODIS. And we can see a number of features that get discussed a lot in the literature. in the Northern Hemisphere, looking over populated regions, we see this decrease in AOD and decrease in the clear sky reflection that's consistent with emissions regulations and a decrease in anthropogenic aerosol, as well as kind of this huge increase in AOD and brightening over, say India, where there's been a rapid industrialization over this century. But what stood out to me is in this region that I've boxed here in the Southern Ocean, this increase in aerosol there and this consistent brightening that's pretty uniform and widespread and doesn't quite make sense to attribute to changes in anthropogenic activity because this is a region where there are no people living. So over the Southern Ocean, most of the aerosols come from the ocean itself. This is primarily sea salt aerosol, with some contribution from organics and sulfate. And these aerosols are emitted when wind blows over the ocean, generates waves and sea spray. And so, as we expect, if we look at kind of anomalies in the Southern Ocean aerosol optical depth, these are correlated with anomalies in wind speeds over this region. And so then, my very first hypothesis was, okay, well, if the winds are generating these sea salt aerosol emissions, then maybe it's the winds that have been changing to cause this increase in AOD. And that explanation seems to hold true. So when we look over the Southern Ocean region, we see that the near surface wind speeds have in fact been increasing quite robustly over the past 23 years or so, especially in the summer, which is what I'm focusing here on because that is when there is insolation and when the albedo is relevant. So the wind speeds have been increasing, leading to this increase in aerosol optical depth and the subsequent brightening or greater reflection by the clear sky atmosphere. So that is the really simple story, that increased wind speeds lead to more emission of sea spray aerosol, greater reflectivity, and that kind of ties back around then into being this really important contribution to what's driving this trend away from what we have observed as this really surprising symmetry of albedo between the two hemispheres. If we want to understand why that's been changing, we have to understand both that the northern hemisphere clear sky albedo has been decreasing, largely driven by anthropogenic changes, but also that the southern hemisphere clear sky albedo has been increasing due to these kind of natural emissions of sea spray aerosol. What has been driving these wind speeds is kind of a bit out of the scope of this study, but there's been lots of other work attributing this to both changes in ozone and CO2. What exactly is going on in this specific time period, I think is still a bit of an open question. And yeah, I think I will stop here. And as I said, the paper just came out. You can read it here, or follow up with me via email, and I'm happy to take questions now. Thanks.
Great, thanks, Claire, for a great talk. We have a question from Rob in the chat.
Yeah, very interesting, Claire. Yeah, I'm just curious about, because you'd expect DMS increases to also be driven by increasing wind speed just through the surface fluxes, and that would drive increased sulfate aerosol, well, it might drive increased aerosol sulfate production. I'm curious if the model should have some of that in it, I think, but I'm just curious if you've looked at that.
Yeah, so for the speciation of aerosol, I'm using the Aero 5 CAMS reanalysis. So this is constrained with the MODIS total AOD, but then it's doing the speciation all with a model. So take that with a big grain of salt, I would say, pun intended. But you can. So the wind speed is definitely a strong driver of the sea salt AOD in that model. It's kind of a weak driver of sulfate AOD. I guess because there's also other sources of sulfate beyond DMS, but certainly, yeah, the wind speeds are correlated with the sulfate as well.
Yeah, thanks. Yeah, it seems like it's in this it's dominated by the sea salt, but yeah.
Yeah, but as I said, I think this is not this is not really a true observation by any means with the Air 5 cams. I wanted to really look into this using, say, the Modus Fine and coarse mode AOD, but that product is just not robust enough, I think, to really trust for this kind of analysis either.
Yeah, and then I guess there's also a question of how well it can simulate the natural sulfate production of aerosol anyway in the model. It's kind of complicated, involving, clouds and
Yeah.
all kinds of things. Yeah. All right. Thank you.
Mhm.
Great. So if there's no further questions for Claire, then we can move on to the final discussion where anyone can ask. Actually, Maria has a question, so perhaps Maria, you would like to ask that question unmuted? Or I can read it. Or
I'm seeing it. Okay, hemisphere
okay, or Claire can read it.
is back to 0. Would the last few months be a test of whether it's a central player in the symmetry problem? That's a good question, Maria. I think, yeah, I guess there's a few things to say. This is not, any even close to proof that this symmetry doesn't exist or anything. It's, I guess, saying that on some certain time scale, you can have these long-term deviations that seem to be driven by aerosol changes, and that the cloud changes have not kind of compensated in a way that these symmetry mechanisms might suggest they should. But maybe, if we keep waiting long enough, and maybe we even, one more year of observations is going to be enough waiting time to see that kind of cloud response adjust us back into a symmetric state. So I think it's definitely something to keep looking at. Thanks.
Great. Yes, Gavin.
Hi, Claire. Very interesting talk. But if you go back to the original question, why would the albedo be the same, right? For that to be some kind of fundamental thing, there has to be a feedback mechanism by which an increase in albedo in one hemisphere leads to an increase in albedo in the other hemisphere, or vice versa, right? And so, one can think about certain kinds of phenomena that would work, right? So if you had increase in albedo because of aerosols in the northern hemisphere, that pushes the ITCZ south, and so that makes the southern hemisphere albedo larger as well because you've got a cloud compensating for the aerosols, right? But when you come to something like the wind patterns around the Southern Ocean, right? I don't know that there's any mechanism that would compensate for an ozone hole forming and the winds speeding up and that changing the aerosols, and therefore something else then happening, right, to compensate for it, right? I mean, do you have any you've thought about this for much longer than me, so what do you think? Is this a fundamental thing, or is it just a random coincidence for the time that we're actually in?
I don't think I can actually answer that question, but I think that working on this project has definitely swayed me more into the realm that this doesn't have to be any fundamental property, that because we're seeing these deviations that are driven by, as you're saying, these processes that don't have any kind of clear compensating mechanisms built in, that maybe we are just observing kind of a special time. On the other hand, I think there are a whole host of possible feedback processes that you could get from having enhanced sea spray aerosol over the Southern Ocean that have to do with kind of local changes of Southern Ocean clouds, because of course this is a super cloudy region, and so putting more CCN into the atmosphere could change the clouds there could change precipitation, could have
That would
other
go the wrong
downstream
way,
effects
wouldn't it,
too.
though?
Yeah.
If you have more sea salt aerosols, you have more clouds.
Right.
So that's backwards.
Yeah, that is not a compensating thing, but maybe then those clouds will have, some changes on the tropical on tropical clouds. And, I think the system is a complicated, intertwined place. So I'm
Yeah.
not saying that this proves anything one way or the other, but it definitely looking into these observations and seeing this deviation over time that's driven by these kind of more external aerosol processes and not being compensated, at least on these timescales, by clouds. But as Maria says, maybe on longer timescales, clouds will adjust. It's, yeah, still an open question.
Okay, thank you.
If anybody has any questions for any of the speakers, now is the time to ask. I can ask a question. Nobody has any questions. I had a question for Moritz about your land and ocean simulations. And I think it's possible that you maybe kind of answered this, and maybe it was in the chat. But you had some pretty significant cooling also over the land, especially in Africa, and I was wondering if you could talk more about that.
Yeah, I think you're referring, I'm not going to bring up the figure, but in the
Okay.
simulation, CO2 forcing over land, you're right, you see kind of a dipole over Africa. So there's like over Saharan Africa, there's like a cooling, and then to the north of it, there's a heating. And I think this is related to shifts in the monsoon. So you're basically bringing in a lot of net energy imbalance to the atmosphere over Africa, and that the monsoon kind of depends on this. I don't have a better answer to this than this hand wavy. It has to do with the monsoon, but I'm quite convinced that it does have to do with this. You also see it in the precipitation pattern. Yeah.
Well, yeah.
So I think if you get more rain there, this can actually cool the African land.
Great. Yeah. Does anybody else have any questions for any of the participants?